the sister based on their knowledge. In this poster, we present an interactive system for biologists to help with analyzing the development of clone embryo.
This project looked at charts submitted by U.S. public companies in annual 10K reports. The most common chart types were identified, and the more unusual types tested in an experiment. Participants were unsuccessful with scatter or relative waterfall charts, but successful with stacked bar and combo charts. Several design flaws were identified and verified experimentally. Overall, the study shows the need to improve financial chart design.
As visualizations begin to use color, shape, line, and form in new ways, legends often go overlooked as essential to interpretation. To address this issue, we created a web-based interface that renders and formats legend entries, presenting the dynamic properties of glyphs, lines, and surfaces, and increasing nuanced object recognition in artist-driven 3D scientific visualizations. Each legend entry includes the variable name, full value range, and artist-chosen artifact.
The most impactful and effective visualizations through history are often visually complex, thought-provoking, and not amenable to quick glances of information. Yet, in our teaching, our experiments, and our textbooks, we often advise people that the most effective visualizations are those where we get information as quickly as possible, like in scatter plots. Why this disconnect? Why aren't all visualizations scatter plots?
This work presents a detailed account of an attempt to explain tightly coupled relationships through storytelling and animation in a multi-user, informal learning environment to a public with varying prior knowledge on the domain and identifies lessons for future design. It offers qualitative empirical findings with particular emphasis on how, despite careful design, visitors may walk away with little knowledge about the data and the problem.
Urban traffic congestion has become an important problem. Previous studies have focused on detecting traffic congestion and predicting future trends. However, it is difficult to find research that identifies the causes of traffic congestion. In this paper, we propose a technique to analyze the cause of traffic congestion based on the traffic flow theory.
To uncover football tactics, we create spaces and times. We use time query, construct spaces, construct times. Our approach was used for reconstructing team tactics in different classes of game situations. Our domain experts are happy, and the Germans shall win again and again.
A short overview of the presentation for a simple pipeline for coherent grid maps. In a grid map, we transform an input map to a tile arrangement. However, current approaches do not perform well on complex maps such as the Netherlands. We propose a pipeline that generates high quality and coherent grid maps even for complex data using a simple pipeline.
Political debates are a rare opportunity for voters to learn valuable information about candidates and their stances on important issues, but they can also be inaccessible for casual, non-expert users. Through a 2-year design study in collaboration with political scientists and journalists, we created a novel task analysis for exploring transcripts as a casual user and developed DebateViz, an interactive tool for visualizing political debates for casual, non-expert users.
Ensuring the usability of a dataset is often tied to data wrangling. We can use provenance to log the employed steps, but these alone will not give us meaningful insights if data quality was improved. We propose to incorporate data quality metrics into the provenance model. The enhanced provenance graph can be visualized to show the development of quality throughout the wrangling process. To find out more about the visualization design and the results of our evaluation, please join us during the live presentation and discussion session.
Mode surfaces are the generalization of degenerate curves and neutral surfaces. In this paper, we provide novel analysis on the topological structures of mode surfaces. This allows us to not only better understand the structures in mode surfaces and their interactions with degenerate curves and neutral surfaces, but also develop an efficient algorithm to seamlessly extract mode surfaces. We apply our analysis and visualization to a number of solid mechanics data sets.
We study the limitations of node-link diagrams with respect to pathfinding tasks. But wait, I hear you say, hasn't that been studied before? Actually, no. Past studies typically measure only accuracy and time for fixed network sizes. We used a number of physiological measures, including brain activity, and looked at a range of network sizes and densities. We discovered that the threshold for difficulty is much lower than expected. This talk is essential viewing for anyone interested in network visualization design.
The recent technological advancements in mixed reality extend our ability to evaluate new visualizations faster than ever before. In a user study with 60 participants, we compared 4 situated visualizations using 5 different empirical methods. In contrast to prior work, our results showed no dependency between the user's feedback and the empirical methods.
Over hundreds of tools exist for visualizing genomics data, leaving the analysts with a large design space to analyze before finalizing the visualization. We present a data and task-based recommendation system. The recommendation system uses a sequential model to suggest appropriate visualizations to users. To learn more about our recommendation methodology and results, please visit our poster.
Chiroplast maps are popular. However, we have better encodings for numeric values. Check out the prism map. Worry about occlusion and perspective distortion? Let's go immersive. Want to have both of them? We present tilt map, a novel interaction technique for transitioning from a chiroplast map to a prism map to a bar chart to overcome the limitations of each. Believe me, tilt map opens up many research possibilities.
Our paper describes the motivation, ideation, and prototyping of a novel visualization tool to support voice training for transgender people. We centered our design around user needs and lived experiences in order to support self-determination of gender expression. In so doing, we made novel inroads in how to visualize speech data and opened possibilities for future work in the design of visualizations that prioritize user agency.
Hello, we are presenting deep volumetric ambient occlusion, a novel technique for deep learning-based ambient occlusion in volume rendering. In our talk,
Hello, everyone. It's a pleasure for me to introduce you all to this session of time here at the WIS conference, in the virtual WIS conference. My name is Jürgen Bernhard. I had the pleasure to be here in this venue in the time session in 2013 for the first time. For those who don't know me, I have been working with Tamara Munson at UBC in the last 2 years as a postdoc, and I'm now at the University of Zurich as an assistant professor. And coming back from me to the main track, I would like to introduce you to six wonderful papers, different topics about time, different data types. Many famous researchers involved, but also some new faces, applications, theory, a lot of stuff. And I would like to start with the first paper, which is presented by Takanori Fujiwara from the University of California. This is joint work that he's doing together with his colleagues from Kobe University and Riken RCCS. The paper title is Visual Analysis Framework for Reviewing Multivariate Time Series Data with Dimensionality Reduction. And it's not about the univariate time series, it's not about multivariate time series, but it's about multiple multivariate time series. And here we go.
Hello everyone, I'm Takanori Fujiwara from UC Davis. Today I will be talking about a visual analytics framework for reviewing multivariate time series data with dimensionality reduction. Multivariate time series analysis is becoming increasingly important in many application domains, such as healthcare and car transportation. As seen in the emergence of the Internet of Things, the size and dimensions of available data are becoming larger, and this makes the analysis of multi-time series data more challenging. To analyze such large and high-dimensional data, dimensionality reduction is frequently used as it can provide succinct overview of the data. Existing dimensionality reduction methods such as PCA and t-SNE are designed to apply to a matrix. However, in multivariate time series data, multiple instances which have multiple variables change their values over time, and thus it is often represented as a third-order tensor. As a result, we cannot directly apply existing dimensionality reduction methods to the entire data. Therefore, typically the researchers slice the data along a time axis, then apply dimensionality reduction to each slice and show each result with animation or juxtaposition. Another approach is computing each slice's dissimilarities with a certain distance measure, and then producing the dimensionality reduction result based on their dissimilarities. Slicing can be applied to the other axes as well. For example, we can perform a slicing the data along a variable axis and follow the same procedure above. However, these existing approaches have several limitations. When there are many slices and we use animation or juxtaposition, it is difficult to find important patterns such as similar temporal patterns and outliers. Applying dimensionality reduction to dissimilarities of matrices does not have this problem. However, when computing the dissimilarities, this approach mixes up different axes such as time points and variables. As a result, we might not be able to find any useful patterns that are highly related to a specific axis. For concrete example, please refer to our paper. Additionally, both approaches usually have limited support of interpretability of the results. To overcome these limitations, we designed multi-DR framework, which has two major functionalities. First, multi-DR framework provides a two-step dimensionality reduction. Unlike the approach using animation or juxtaposition, the two-step dimensionality reduction uses all axes to produce the results. Also, it handles each axis separately. Consequently, we can avoid mixing up different axes. Additionally, we support interpretability by using contrastive learning with an interactive visualization. In this approach, we can provide algorithmic support to understand dimensionality reduction results. I will now explain the details of each functionality. First, I will explain the two-step dimensionality reduction. Here, we have a tensor of t time points, n instances, and d variables. We first apply tensor unfolding, which reshapes the input tensor to a matrix of n times t rows and d columns by arranging vectors obtained from slicing along both the time and instance axes. Then, we apply dimensionality reduction to the obtained matrix to reduce d columns to 1 column. After that, by referring to the index information of time points and instances, we can produce a matrix of n rows and t columns. The purpose of this first dimensionality reduction is to compress the multiple variables to one representative variable while preserving certain information as much as possible. For this step, based on the analysis purpose, we can select a linear dimensionality reduction method. For example, we can use PCA to preserve the variance information, or LDA to include the differences from the other tensors. Now, we can apply any dimensionality reduction method to this produced matrix. This step produces a low-dimensional representation for visualization purposes. Again, based on the analysis purpose, we can select any method for this step, such as PCA, t-SNE, and UMAP. For the rest of the slides, I will use PCA and UMAP as the first and second dimensionality reduction methods, respectively. In the previous slide, we obtained instance similarities by applying the first and second dimensionality reduction to the variables and time axis, respectively. Because we apply the second dimensionality reduction to the time axis, the obtained results show the instance similarities mainly based on temporal changes. Similarly, we can apply dimensionality reduction in a different order. In this case, instance similarities are mainly based on distribution differences in variables. For example, when we analyze the US air quality data, we can obtain two different dissimilarity results of US counties. On the left, the second dimensionality reduction is applied to the time axis. So this shows the similarities of counties mainly based on weekly changes of air quality. On the other hand, on the right, the second dimensionality reduction is applied to the variable axis. As a result, this shows the similarities of counties based on overall values of air quality measures across time. Similarly, we can obtain different results of similarities of time points and variables as well. Now, I will explain how multi-DR provides interpretability. We first provide the related context of points showing the dimensionality reduction results. For example, when we analyzing similarities of US counties, we can provide location information. By linking these views, we can show which counties are included in each cluster. For the further analysis, we usually want to know the characteristics of each cluster. To support this task, we visualize the features contributions to characteristics of each cluster. To provide such information, we utilize contrastive learning. More specifically, we use CCPCA with our new sign adjustment algorithm. Please refer to our paper for more details. We visualize feature contributions corresponding to each dimensionality reduction result. In this example, this plot shows each week's feature contributions. The magnitude of the value represents the strength of the contributions, and each sign shows whether a cluster tends to have higher or lower feature values compared to the other points. Here, we can see the blue and orange clusters have different peaks in their feature contributions. We also show relative frequency histograms of selected features to compare value distributions across the clusters. We can see that when a cluster has a high feature contribution, we can see more distinct distributions. We also want to know the meaning of the feature values. For this, we visualize weight vectors that the first dimensionality reduction uses to generate the representative feature. In this example, we can see that all measures except for ozone have similar weights. Thus, we can say that the feature values are close to the mean of the four measures with similar weights. In summary, we provide three pieces of information to support interpretability of the two-step dimensionality reduction results. Now, I will demonstrate one representative case study. In this case study, we analyze a dynamic contact network of high school students. From the network, we extract the variables with DeepGL, which is a network representation learning method. DeepGL produces 10 features which consist of node attributes, network centralities, and others. As a result, we obtain a tensor of 30 time points, 180 instances, and 10 variables. From the obtained tensor, we identify and characterize different groups of students. The right result shows the similarities of students based on node features. Here, we select several distinct clusters to analyze their characteristics in more detail. From the node link diagram, which shows all communications throughout the entire period, we can see students in the blue cluster are located in the strongly connected regions. In contrast, students in the teal cluster have only few connections to others. In the feature contribution view, for each network centrality, the blue and orange clusters generally have strong positive contributions. By selecting several features, we can see that the blue and orange cluster tend to have higher values compared to that of the others. This is especially more salient for the blue cluster. From the weight vector, we notice that these generated features use large weight around the morning, whereas evening has close to zero weight. MultiDL seems to effectively prioritize the time when students have actively contacted each other more. From the analysis, we can say that during school hours, the students in blue cluster play a central role in communicating to other students as they have higher values for various network centralities. Now, we further categorize these students from this left side view, which shows the similarities of students based on their temporal communication patterns. In this view, each cluster is generally arranged from left to right. However, we can see the blue cluster is separated into two clusters. We select these two as the new clusters. In the node link diagram, these clusters are clearly separated into the two strongly connected regions at the top and the bottom of the view. We also can see that the two clusters have different patterns of feature contributions across time. By looking at the histograms at each time point, we can see that they have high feature values at different time periods. Also, from the weight vector, we notice that the feature values represent the network centralities, but not gender. From these observations, the students who play a central role can be further categorized into two different groups, which have active communications at different time periods. Due to the time limitation, I presented only one example, but you can find more cases in the paper. One of which we provide an analysis of large-scale log data obtained from the supercomputer K. You can also find a qualitative comparison of the two-step dimensionality reduction to other methods. Finally, I'd like to conclude my talk. This work presents a framework called MultiDR, which has two functionalities derived from a two-step dimensionality reduction, contrastive learning, and interactive visualization. We use MultiDL to analyze multivariate time series data. However, MultiDL can analyze any data that can be represented as a third-order tensor. Lastly, the source code is available on GitHub. Thank you for listening.
Thank you, Takanori, for this interesting talk. It was enlightening as you are bringing up three different aspects as opposed to two if you have only one multivariate time series. We have time for questions. Let me see if Discord has questions so far. Let's start with this one. How would you adjust the detection of temporal patterns over the time zones, north versus south hemisphere?
Yeah, I think I didn't care about when I'm analyzing that because like my case like already time zone is fixed in some global like universal time zone, so I didn't care about that. But yeah, maybe in the future I need to consider about those time zone differences maybe.
I guess it will add even more complexity to it.
Yeah.
I would like to add a question regarding this complexity, as you're having three different things, different instances, different timestamps, and different variables. That was totally clear to me and conceptually interesting. What I had problems with when reading the paper is that everything ends up in different scatter plots and with different steps in the processes using different DR techniques. Did you discover any problems about users about the intuitiveness of the complex visual representation that you use?
So I think so when I was asked to use this system, my friend or other collaborators, they at first like they somewhat confused about because we use two-step dimensionality reduction. So how they act for the first one, how they act to the second one. So but like once you understood how it works, still they can understand. So I mean, like of course there is some learning curve because you are trying to understand complex behaviors. But visual representation was everything. Like they don't have so many problems. Actually. Yeah.
I guess that there may be a curve. Exactly. There's one last question. Please answer quickly if you can. Can you apply this to graphs?
Yes, actually, I applied to the graphs in my case studies because like even graph doesn't have attributes in originally, but you can extract the attributes by using some network representation learning. Actually, in my case study, I use DeepGL.
Ending up in a three-dimensional abstract space, and then you do the process again. Got it. I would like to thank you again and continue with the next paper. Thank you.
Thank you.
And the second paper is presented by Ziming Zheng. He is at the School of Data Science in Fudan University of China, and he is presenting joint work together with Natalia and Gennady Andrienko from the Fraunhofer IIS in Germany. Also Ji Li, who is in Jianying University, and with Xiaoru Yuan at the Peking University. The title is Co-Bridges, Pairwise Visual Connection and Comparison of Multi-Item Data Streams. And I would like to spoil you that we will now give full steam to the comparison of sequences of multi-item data. Yay.
Everyone, this is Siming from Fudan University. Today, I would like to present our work Co-Bridges, Pairwise Visual Connection and Comparison for Multi-Item Data Streams. Our co-authors are Natalia, Gennady, Jie, and Xiaoru. So our motivation comes from this, how to compare the multi-item data streams. So the multi-item data streams are really very diverse here, like social media text streams or dynamic event streams or gene sequence. So these items can be like text in the text stream or the event in the event streams and like the genes in the gene sequence. So in the example for social media text streams, we want to do the comparison to understand here is the Hillary Clinton and Donald Trump's tweets in the president election. If we want to know what are the keyword difference from these two people, then how different is the frequency and who prefers more in which time. So these questions are about the comparison of these multi-items, like the multiple text. So directly we cannot get the idea of this task. So the challenges here is because there are various types of data streams with these dynamic characters and hard cardinality of the data items. Also, if we want to compare the multiple perspectives, so this is really challenging. So our focus here is a pairwise comparison, which means we only compare two streams in details. So to achieve a comparison, what we need is first we need to align it. So need to align the things we want to compare and show the correspondence part for items and sequential information. This figure is the photos that I took in Florence when I visit there. So you can see here on the left part and right part, can we put some items of the streams there, and also for bridges, should it be the correspondence and connections for the comparison? And also connecting with the visualization tradition that we use stream graphs for indicating the stream data or dynamic data. So we can combine it to use the bridges and the river metaphors for the comparisons. But how? So we propose such a metaphor. Here it includes the river and bridges. So you can see we can put the river on the left and right side, indicates the total amount of the streams and the dynamic features. And in each part, we can use the bridge to connect and correspondence to show the correspondence part, indicating the different items distribution. So we put the important items, both sides of the data shared here. You can see this item 1 is more mentioned by the left part street, but the item 3 that mentioned more about from the stream B. So with this quite simple metaphor, but I think it's effective to do the connection and showing the correspondence, and do the comparison. So that's why we call it co-bridges. So let's see the comparison tasks, how the co-bridges can solve that. We can show the dynamic numeric traits, and also we provide a different levels of granularity. Also, we can support the comparison of the qualitative comparison to show the common or distinct items. Also, we can conduct quantitative comparison to understand relative frequencies and absolute amounts here. So we use the illustrating data to illustrate our co-bridges design. This is data from the tweets and showing the Hillary Clinton and Donald Trump. The pink one is the Hillary Clinton and the blue one is the Donald Trump. So we can see in the 2016 president elections, we can conduct the comparisons. In this illustration, we select the job issues and want to compare different contextual word usage when discussing the jobs issue between the two users. From top to bottom, the user's timeline are laid out as a bank of a river. The curves indicate the amount of related tweets. In each week, a bridge is connected between the two sides, showing the different frequent keywords used by the two users. Each word is colored by two portions, indicating the ratio of each user's usage. The weight of each word shows the times of usage. The more one user mentions a word, it will be put more towards the side of the user. The weight of the bridge encodes the total amount of words. So the design details are the alignment by the time sequence, and more importantly, we do the visual encoding supporting the comparison. So the size here encodes the absolute amount of the item. Here is the absolute amount of the text frequency, and then the order is based on the absolute difference. So here we can supporting the comparing the qualitative design comparison and the quantitative comparison. We can see here the grid comes more on the right part, but also like in second week, Hillary Clinton also mentioned a lot about the grid and to pull these words into the middle. So with this, we can observing the Chen patterns to these comparisons. Also, we propose a visual analytic system supporting this comparison task, including the graph view, co-bridges views, and the detail views. So this is the exploration pipeline, which includes the comparison entry that we support the text query and a graph node brush to find the keywords to compare and showing the contextual keywords of these keywords. And then we also can support attribute filtering from exploratory results and conduct the detail level visual comparison, including the semantic zooming and detail on demand. And afterwards, we conduct a comparison of a comparison. So the comparison of comparison is the higher level of comparison patterns that after we explore some important or meaningful keywords, like America, families, great, and America first, we can see the overall trend patterns. From the Hillary Clinton mentioned more about America, families, but Trump mentioned more about great in different time period, and or even Trump creates this America first, only he used it. So let's see the video to how to explore this. We propose a visual analytics system supporting visual comparison. In the graph view, it shows the frequent items and its concurrent relationship, enable a comparison entrance. Besides the call bridges view and detail view, we also provide a view showing comparison of comparisons. In this case, we will investigate how Clinton and Trump talk about each other. First, we select Donald and compare the subtextual strings containing Donald. We can see Clinton mentioned these words much more and several words together used by her. For example, we notice text is often mentioned and drill down to these words, and find Clinton attacked Trump on his tax issue and tax plans, mentioning tweets like, "Just released my tax returns," and "Donald, where are yours?" So we mark these findings as text. Then we come back to the last view, and words like anti or LGBT were mentioned often by Clinton in the period. We checked the tweet and found she mentioned pens. Then we type in pens and query the subset containing pens and found an interesting pattern. Clinton attacked pens on anti-LGBT and Trump defended using Trump Pens 16 to advocate his campaign. We drill down to the peak week and examine the daily patterns. We've also found the Clinton attack pens on slashing education fundings. So the interesting findings of pens is also marked. Then we go back to the overview and examine the tweets containing Clinton. Surprisingly different from the previous pattern, in some weeks, Clinton is laid out in the middle of the bridges. We first examine Trump, what Trump's talk about, and select the outstanding word crooked. He mentioned crooked together with Clinton many times, especially from July to August. He even created a hashtag called crooked Hillary. So we also mark this finding. And we identify some other similar words Trump often used, like bad. He said bad Clinton, bad media, or bad New York Times. We select the New York Times and found the words falling. And then explore CNN in the Chen. He attacked CNN and Clinton at the same time in several tweets. In this iterative exploration, we identify how Trump attacked Clinton. On the other side, we are curious about what Clinton mentioned about herself. Clinton was reposting the reports praising herself from other social media users or social media accounts, like photos, with most of the good words. In the comparison of comparison view, we can identify the different patterns of comparisons what we find just now. We can also drill down to details and compare the final patterns in this view by selecting the period. And the narratives can be summarized from the July 13 to August 3rd. Trump and Clinton's attack and defense happens in the interesting time patterns. To summarize from this exploration case, so we have showing the virtual board battles between Hillary Clinton and Donald Trump. So Clinton attacks on tax issue first, and then the attack on the pens, and Trump defended. And from the Trump side, Trump attacked Clinton on the CNN and crooked Hillary, and then also Clinton defends by quoting the media about the Clinton, good words about Clinton. So with this, we can also conduct a comparison of comparisons showing these virtual petals. And also we conduct an evaluation to understand the user's understanding and the effectiveness of the code bridges. We conducted a control study for comparing code bridges against the baseline using Twitter data and the football events data. So we recruit 36 participants and subdivide them randomly into 2 groups. Each one has 18 people. And both of them do 2 studies for this, 1 data set with 1 metaphor. So the baseline looks like this. We keep the beta consistent, we keep the timeline design, and we use the histograms here. And the height indicates the frequencies, and order is the same as our coverages, but using the absolute in the global scales. And we provide 8 tasks, including mentioning about Chen comparison, qualitative and quantitative comparisons, and we evaluate the accuracies and the completion times. And also we conduct evaluation with the football event sequence. So we certificate that our coverage design is diverse, is general, that not only can apply for tweet data, but also the football event sequence. And we get the results as for the accuracy rate of a Twitter dataset, which is more complex. The coverages have significant higher accuracies more than a baseline, and others they perform equally. And also the subjective feedbacks is better from the coverage size, that is easier to understand and compare, and also authentic appearance. So to conclude, our solution is this. We propose these code bridges as a general method for multi-item data streams comparisons. We can connect the corresponding parts in the to pairwise data streams and conduct supporting the comparisons. So thank you very much.
Thank you, Seming, for this interesting talk. Very nice idea to apply this metaphor for streaming data. While we are waiting, applause, by the way, from the audience. While we are waiting for questions, you could tell us who will win the president election for next time. No, please don't answer that. I will start with a question in the meantime. When I read the paper and I looked at the metaphor for the first time, I had the opportunity to think what I see as opposed to what you describe. And what I did wrong is to see the overall width as a visual encoding of something, as opposed to the width that is on the sides, which actually means the word count. Did you experience that other users had similar problems?
Yes, you mean the width and the overall size is a bit confusing. Yeah, because that we want to just for in each aggregation time, we have the size to compare for the word inside, but across multiple weeks, then we can have the size as the overall comparison. And yeah, that's a little bit confusing. We will improve it a bit, but yeah, current situation, it can still provide a sense that which word is mentioning more in the overall, because the overall size is from the width plus the width multiple the height. So it's yeah, it provides an indication of the overall.
Got that. Very quick answer to the second question, which comes from Maria Zemakova, which is, can you apply it to more than 2 streams at the same time? Or have any thoughts about that?
Yes, there we are trying to extend it to more, but current situation that we only support 2 because we use the pairwise ones, but we want to extend it a bit more like a bit like pair coordinates things, then we can compare multiple things. Yeah, that's a direction.
Okay, this will be a bunch of beautiful colors and shapes. Okay, let us know how far you get with this. And with this, I would like to thank you, Simi, once again.
Thank you very much.
And we wait for the third paper. Coming back to the third paper, and I would like to start with the title, which is MultiSegVA using visual analytics to segment biologging time series on multiple scales. It is presented by Philipp Meschenmoser, who is at the University of Constance, and this work is together with his colleague Juri, Buchmuller, Daniel Seebacher, and Daniel Keim, all from Constance. And there is a guest author who is from the Max Planck Institute for Animal Behavior, which is Martin Wikelski. So let's segment some biologging time series.
Hello, I'm Philipp from the University of Constance. Today I welcome you to my talk about our MultiSegVA platform, where we use visual analytics to easily segment biologging time series on multiple scales. This is a joint work with my colleagues Juri Buchmuller, Daniel Seebacher, Daniel Keim, as well as with Martin Wikelski from the Max Planck Institute of Animal Behavior. About our motivation, the recent advances in sensor technology are leading us to an entirely new era of understanding animal behaviors. Billions of high-resolution GPS and acceleration records from biologging tags can help in better understanding and addressing some of the most urgent problems of our time. Climate change, species decline, disease transmission, for example. The resulting biologging time series have then behaviors on very different temporal and spatial scales that need to be distinguished. Think of annual migrations or micro-movement frames. So, considering these scales with their specific properties during the essential task of segmentation is important, but it is often avoided or impeded by several factors. First, multiscale analyses require the careful parametrization of scale settings and scale-wise techniques. For a movement ecologist, this aspect often implies the need for cross-domain expertise in fields such as multiscale time series statistics. But in particular, there is no tailored visual active tool to explore results and refine parameters in the context of multiscale time series segmentation. Further impeding factors are inflexible analysis means. Typically, it comes to the inflexible chaining of individual R or Python scripts. To address this problem statement, we present our MultiSegVA platform that comes with 3 major contributions. As a primary contribution, we use tailored and extensive visual interactive features in the context of multiscale time series segmentation. Second, we contribute a new visual query language to flexibly configure segmentation techniques on various temporal scales. As a third contribution, this VQL consumes a domain-oriented set of techniques that was compiled together with experts in movement ecology. With these contributions, we fulfill 4 major requirements that were derived together with our experts from the Max Planck Institute of Animal Behavior. MultiSegVA integrates diverse techniques into one approach, shows multiscale structures and specifics, enables a flexible parametrization, and has extensive tailored visual interactive features. No related approach fulfills all 4 requirements, and our approach is in addition compatible with heterogeneous data, is well generalizable, and it provides the geocontext. Now we give a quick overview on our web-based platform MultiSegVA. There are 3 ways to import a time series to our platform. In particular, we provide a linkage to the MoveBank, that is an online repository with billions of animal locations. After import, the time series appears in one main window that contains our VQL, a segment re-encoding by a tailored icicle visualization, and hence a visual overview. The analyst can forward a segment to additional detail windows in further browser tabs, for example to get insights about local anomalies or their geocontext. Finally, a semi-automatically annotated segment tree and the visual query can be exported. Given our scheme, the input and output features make the seamless integration to existing workflows possible. In addition, the multi-window feature enables simultaneous analysis on multiple computers. In the following, we demonstrate MultiSegVA by a use case about environment-aware behavior analysis of Himalayan vultures. These animals belong to the heaviest flying birds, but still they manage outstanding altitudinal migrations. Our movement ecologists investigate how the vultures exploit different environmental conditions to migrate and fly on high altitudes with a minimum energy expenditure. Initially, the analyst imports and visually explores a biologging time series with dimensions for location, 3D acceleration and environmental conditions. To distinguish migration stages in almost 800,000 records, the analyst considers our VQL and applies at the first temporal scale level change point detection in the altitude dimension. The resulting segments are given in the interlinked top visualization, and a sibling-based color scheme is guiding to possible patterns and anomalies. By a simple right-click, a segment can be forwarded to the geographical detail window. Here we can see the entire trajectory, with the forwarded segment highlighted, and observe the altitudinal migration from northern India through the Himalaya to the Tibetan Plateau. Now, the analyst puts the migration into the context of wind conditions and observes correlations between strong orographic uplift and migration. So on scale level 2, the analyst selects value range segmentation at uplift, which is then recursively and locally applied on previous segments. The result is a segment tree encoded by the icicle visualization. To distinguish fly from rest periods on scale level 3, the analyst applies value range segmentation by Y acceleration. The analyst decides for a local growth of the segment tree and focuses a particular high altitude segment with adverse wind conditions. This bookmarking can be also applied automatically. The icicle visualization can be zoomed in to particular segments by one simple click. Also, the synchronization of the below time series plots does not require a cumbersome scrolling of the mouse wheel. Finally, to get temporally coherent activities on level 4, the analyst applies temporal gap detection. Then exports the segment tree and can calculate the environment-aware energy expenditure based on 3D acceleration. By only a few clicks, MultiSegVA enables complex environment-aware analysis with scale-wise parameters and extensive visual feedback. Also, without the inflexible chaining of scripts, MultiSegVA outperforms manual and less detailed annotation work that before has taken several months. Our publication contains another movement ecology use case, namely with data from a local predator that kills billions of mammals per year. Here we show how MultiSegVA can be easily applied for a flexible, progressive clustering. So, at first, segment by temporal gaps to get day-wise behaviors. To exclude an erroneous area, simply draw a polygon, copy its geometry coordinates, and segment recursively by the custom area. After bookmarking some outside areas, density-based clustering on an arbitrary number of upcoming levels can be applied. Finally, apply change point detection at intra-cluster X acceleration. This second use case shows the power of our integrating and visual interactive approach that can link to the clustering paradigm. Lastly, a third use case shows that our approach can be well generalized to other application domains. Here we take the example of power networks. These use cases are complemented by feedback from our experts at the Max Planck Institute of Animal Behavior. MultiSegVA is the outcome of a months-long close collaboration where we could gather highly iterative and valuable feedback in the scope of live sessions. For example, after it was requested by our experts, we could integrate more multivariate features, being essential for 3D acceleration, and a more detailed documentation, as well as upload and export functions. Referring to the expert feedback, MultiSegVA is a clear progress to what is currently available to them. Accordingly, MultiSegVA is a valuable tool that enables them to apply semantically meaningful and fast multiscale analysis. The easy multiscale segmentation and the strong linkage to visual interactive features were perceived as most novel. Our experts see diverse application scenarios, from exploration to the modeling of life histories to video synchronization and validation. Some aspects remain for further reflection. Our VQL is a simple play with building blocks that makes it trivial to build a multiscale segmentation. Rather, it is difficult to decide which techniques and parameters are the most suitable ones on a specific scale. Currently, we support this decision by extensive documentation, categorizations, parameter recommendations, and short processing times in a compact workflow. At upcoming works, we will integrate more methods for recommending techniques and parameters. With these recommendations, we will improve MultiSegVA also by slight data-aware parameter adaptations. For now, a technique at one scale is applied each time with the same parameters. As another aspect, we show a sibling-based guidance variant through the segment tree that optimally captures local similarities. This variant needs relatively more interaction that shall be reduced in upcoming works. Finally, MultiSegVA gives insights into very different semantics. Relations between scales can be better understood, coarse behaviors extracted, and patterns matched by KNN searches. Segment lengths, similarities, local anomalies, and spatial contexts are provided. Yet, broadly capturing deeper behaviors, such as chew or scratch, will require more complex and learning techniques. As it can be seen, our plan is to integrate further intelligent methods at diverse stages to make our platform even more powerful. We present our MultiSegVA platform with its three major contributions. Our work makes semantically meaningful multiscale analysis more accessible, and to quote Spretke et al., it is certainly another step forward to empower the animal tracking community and to foster new insight into the ecology and movement of tracked animals. Saying this, I would like to thank you for your interest and attention. I'm happy to answer your questions now or by mail. Thank you.
Thank you, Philipp. While Sylvia is typing, I hope there's a question coming up. I would like to start with the first question. Interesting work. Thanks for showing this. When I was working with multivariate time series, and you are actually having multivariate time series in your examples, the most critical part was to segment phenomena which are more than univariate, meaning it's some complex thing depending on different dimensions. Do you, and if how do you support this with the tool?
So some of those integrated techniques are already inherently handling multivariate data. For example, that motive detection. Otherwise, another possibility is to use operators, which simply link different outputs of different segmentation techniques. So link the output of technique A on with that dimension, basically. And the third option would be to already import projected or reduced time series where we have fewer dimensions.
So you go down to 1D or so, and then you can see the phenomenon.
For example, yes.
Got it. Wolfgang Eigner has a second question. Maybe, Philipp, you can answer it in the chat because we have to rush for the next paper. Thank you once again, Philipp.
Thank you.
And the next paper is MineTime Insight, visualizing meeting habits to promote informed scheduling decisions. It's presented by Tobias Günther, who has done this work at ETH Zurich together with his colleagues. I'm looking forward to this talk as it will be interesting to see, to learn something about self-monitoring of meeting workload, something that is maybe relevant for every one of us.
Hello everyone and welcome to our presentation of MineTime Insight, a calendar app extension that visualizes meeting habits to promote informed scheduling decisions. In the corporate environment, managers spend up to 70% of their time in meetings, and meetings are quite important. It has been shown that employees who see their managers regularly are more engaged in the company's activities, which is ultimately desirable. In practice, however, and this is something we probably all experienced at some point, meetings with managers can be ineffective. The time that is spent is rather short, things get even worse if there's no clear agenda, and how often meetings take place is usually managed by a personal assistant who is not sitting in the meetings and therefore doesn't really know what the best time frame is to schedule a follow-up. And so the meeting frequency can become inconsistent. Nowadays, meetings are organized in electronic calendars, as shown here. On these calendars, visualizations are optimized for the daily business activities, that is, seeing who to meet next and where to show up. Therefore, calendars offer no support for self-reflection and self-awareness about our scheduling habits over longer periods of time, which is a missed opportunity. So in this work, we want to find out how can calendar views used in a corporate environment be made more appropriate by the use of visualizations to increase the user's self-awareness about the management of their meeting time, including users with little experience in data visualization and analysis. To answer this, we developed a calendar extension with the following goals in mind. First, we want to visually display actionable statistics about the time invested in meetings. For this, we need to quantify the overall time spent on meetings, the time spent with specific people or groups, the frequency and regularity of meetings, and the consistency among and within groups. So everything related to understand the current state. Second, we want to provide tools to set and track goals towards improvement of one's meeting schedule. For this, users need to identify improvement, retrogression, or stagnation towards personal meeting goals, such that actions can be undertaken in order to improve towards the target goals. And finally, we want to make the analysis accessible to a broader audience and find ways to encourage the adoption as part of the daily workflow to achieve a long-term shifting of habits. To be able to reach many users, we implemented our prototype in a cross-platform calendar application called MineTime. MineTime has a modern user interface, a natural language assistant, and uses AI to support you with scheduling suggestions. Now it also contains a time analytics component, which is what I'm presenting to you today. Our MineTime extension provides 4 coordinated views for the analysis of meeting time: the meeting breakdown, the meeting pressure, the periodicity analysis, and the contact diary. The meeting breakdown provides the essential aggregate information about how much time is dedicated to single people or groups of people and enables a simple and immediate visual comparison between them. Thereby, the outer ring of this two-layer sunburst plot encodes the time spent with individuals, whereas the inner ring shows the time spent with groups. The meeting pressure provides a breakdown of the hours invested in meetings over the last month, while providing contextual information on demand. The meeting pressure is visualized as an area chart in which we can see the total time spent in meetings, here in blue, and the fraction of time spent with selected individuals or groups in comparison, here in yellow. The periodicity analysis visualizes how frequently and regularly people have been met in the past, while facilitating the comparison among and within groups. The vertical axis shows how much time passed between the next meeting took place, and the horizontal axis can be interactively reordered to find, for example, the most frequently or most irregularly met individuals. The user can also set own meeting goals for each contact group. We visualize goals in the periodicity analysis and summarize the performance of the user in a single achievement score. And finally, the meeting diary provides details about a specific contact, the most important statistics in textual form, as well as past and future meetings organized in a timeline with space for private notes regarding this person. The meeting diary is also accessible directly from the calendar view and serves as entry point for the analytics view. We also display reminders on the main calendar view to inform the user about people that should be scheduled soon based on the predefined goals. A typical user workflow looks as follows. On the calendar view, the user navigates the weekly calendar, while reminders are displayed on the side for contacts to be seen soon who have not been scheduled yet. The contact diary is displayed on the sidebar whenever an event is selected or when a reminder is clicked. The user can then open the analytics board from the contact diary or with the dedicated button on the main view. On the analytics board, the contact diary can also be opened to provide full contact context without having to leave the view, and using the schedule button, the user triggers the scheduling assistant and is forwarded back to the calendar view. Next, we look at a particular case study. On the left, we see the meeting breakdown with individuals categorized by their email domain, which is an automatically generated proxy for different groups of companies that we generate by default. On the right, we see 4 user-defined groups, and here we see that group 1 in red received most of the attention. Here, the meeting pressure is shown, which was not uniform. Quite a few irregularities can be seen. By consulting with the personal assistants, we found out that most of these gaps here are business trips abroad. The highest meeting pressure on the very right occurred at the end of March. The meeting periodicity analysis shows us how regularly individuals have been met. The first group enjoys frequent and fairly regular meetings. The second group is a little less regular with a very apparent outlier, someone who hasn't been officially met within 6 months. And the last group shows that some individuals have regular, but many also have very irregular meetings. I just wanted to briefly mention that we performed an informal user study with 2 executives, 2 personal assistants, and 4 staff members. All rated the system as useful. Please see the paper for the details on the procedure here. We also conducted a field study with some of the users of MineTime. In a period of about 2 months, about 65 users sent us their feedback. All users analyzed their own calendars, and overall the tool seems most valuable to people who use MineTime in the corporate environment. Again, for the details we refer you to the paper. Finally, I want to make a connection to the field of personal visual analytics, which concentrates on visualizations in a personal context. This includes non-professional situations in which people may have quite different motivations, priorities, role expectations, environments, or time and resource budgets, as compared to professional situations. Even though we target a working environment, there are a number of parallels. First, our user population includes a wide spectrum of users. Second, the usage pattern, although ultimately productivity-oriented, expands beyond the main work role. After all, aside from personal assistants, most people in an office are not hired to manage meetings. Third, the data coming from the user's own calendar is typically considered personal for all but the personal assistants. And fourth, the insight is meant to build awareness about personal scheduling habits and interactions with other employees rather than crystallized analytical conclusions. So we think that this shows that personal visual analytics can also be beneficial for applications in a working environment, at least as long as the data can be considered personal. So, what are the greatest challenges and limitations when designing visualizations of meeting habits to promote informed scheduling decisions? First, the attentional demand needs to be considered. People with low visualization expertise prefer rather simple and well-known visualization techniques. Second, the data quality is often noisy and incomplete, which requires some effort to clean up. And third, the perceived utility varies widely among users depending on their individual requirements regarding meetings, which makes it difficult to tailor a system that fits everyone. As said before, our analytics tool is shipped with the latest version of MineTime. Feel free to try it on your own calendars and see who you forgot to meet. Thank you very much for your attention. I'm looking forward to your questions.
Tobias, thank you for that interesting app. I'm totally interested, such like many other people in the auditory. You already answered one question, which was, is there a link and do you use the tool yourself? And you posted the links. Thanks for that. I know what I will do tonight. I have a main question to you. You say that the tool reminds you of contacts that you forgot to meet. So there is more workload coming up. Oh no, I thought a tool is for reducing workload. Can you please comment on that?
Maybe if you know who you should actually meet, you can reduce the people that you maybe meet too often.
Good point. I'm just copying a question that came in. What do we have here? How is the planning / goal setting done? This is a question that came in earlier. I think it was Wolfgang. Yeah, exactly.
So this can be set for each of the contacts individually, or even per group. And this at the moment is only allowing you to set the desired regularity that you would like to have. So at the moment, we don't have metrics like how productive was the meeting, right? Because there's no easy way to track this.
Yeah, that sounds logical. Yes. I have a last one. You said that it's particularly useful in corporate environments. Does this mean that person A is analyzing the data of person B, or did I misunderstand that? And how does it compare to other environments which are not corporate?
So usually this is meant to analyze your own calendar. So you want to get an idea how you are using your time. And we concentrated here on the corporate world because in this case, the calendar is filled with many people and also with many different contexts. So there's enough interesting data to visualize and analyze.
Yes.
If you have other applications where you also collect similarly rich data, I guess this would also extend in this direction.
Sounds good to me. We are lacking time and so sad because there are many more questions. Maybe Tobias, you can also answer these questions in the chat while we will proceed to the fifth paper. And the next paper is presented by Yuan of the Shandong University. It's called Science Stream, Improving the Readability of Stream Graph by Minimizing Scene Illusion Effects. Co-authors are Quanji Zhang, Quinzheng Wang, Jiang Zhang, Michael Zedelmeier, Oliver Deussen, and Yunghai Wang from the universities of Hong Kong, CENIC, University of Stuttgart, and Constance. So let's learn something about illusions about the vertical thickness in stream graphs.
Hello everyone, my name is Chen, a master student from Shandong University. Today, I'm glad to introduce our work, Science Stream, Improving the Readability of Stream Graphs by Minimizing Sign Illusion Effects. This is our outline. Stream graphs are a variant of stack graphs with a curved baseline to visualize multiple time series data, which are represented by the colored layers in a graph. Compared to stack graphs, the layers of a stream graph are real-like flowing and thus more aesthetically pleasant. Since in 2008, the New York published a stream graph, this visualization is getting more and more popular. One elementary task for a stream graph is reading and comparing the thickness of layers. The difficulty of completing this task directly reflects the readability of a stream graph. Interestingly, psychologists found out that people have difficulties in reading the thickness of distorted layers. In this picture, the thickness of this selected layer doesn't look like it changed very much, while the truth is quite different. Such a distorted layer will severely harm the readability of a stream graph. The reason why users can't perceive the correct thickness is because the human brains perceive the thickness of a region from the horizontal direction instead of the vertical direction. This phenomenon is called sign illusion and was first documented in the context of sinusoidal curves. Due to this illusion, thickness information in stream graphs will be heavily distorted due to the inconsistency between horizontal and vertical direction for the VIS. This way, the sign illusion will directly influence and harm the readability of a stream graph. Through a careful stream graph layout optimization, we can improve its readability by reducing the impact of this illusion. A stream graph is determined by two factors: the layout of the bottommost curve called baseline and the ordering of layers. Different baseline and ordering schemes will let the graph look completely different and affect its readability. We need to take all these two factors into consideration to construct a stream graph, which aims at reducing the impacts of sign illusions. Overall, we want to explore the connection between the sign illusion and the readability of a stream graph. Furthermore, we want to improve the readability of stream graphs by reducing sign illusions. Now, I will briefly introduce some related works. There are many works focused on the enhancement of stream graph readability. They can be classified into two categories. The first is the stream graph layout optimization, which aims at making the graph more easier to read by adjusting the shape of the baseline and by ordering layers. Such methods try to reduce the distortion of layers and then make the graphs more easier to read. But the proposed algorithms are obtained through observation or experience and make a perceptual foundation. The second category is the interactive editing of stream graphs. By applying interactive layout adjustments, the queries are central to stream graphs. Such measures can mitigate perceptual issues and improve readability. While they are very effective, such interactions can be applied to statistical visualization and don't allow to create good stream graphs automatically. Now, let's meet our method. Our idea is the following. As the sign illusion will affect the readability of a stream graph through the perceptual inconsistency between orthogonal and vertical widths of a layer. We try to align the orthogonal and vertical thickness as much as possible. During our mathematical analysis, we found out that this can be reached by restricting the upper and lower boundaries of a layer to have the same slope but different sign. In other words, we aim to make the layer slope as close to 0 as possible. This allows us to get a baseline formula, and as a matter of fact, it is the same solution as already found by Baron, even though they didn't consider Saint-Laurent as a driving factor. In addition, this baseline formula allows us to get visual pleasant results. But there is a problem with Baron's formulation. An inappropriate weight selection for the layers within his formula does allow to reduce the impact of Saint-Laurent for combined layers. Then simply use the layer thickness as a weight for each layer. However, as we can see, when the thickness of a singlet layers changes very much, it will squeeze its neighbors and introduce distortions there, and the Saint-Laurent on these neighbor layers will increase at the same time. In order to avoid such a situation, we use the Gaussian weighting scheme to balance the weight of single layers when their thickness has a drastic change. This allows us to reduce Saint-Laurents for the whole string graph and create a better overall result. In addition to baseline optimization, another factor that determines the layout of a string graph is the ordering of layers. We can say that with the same baseline but different orderings, the readability of a string graph is very different. In the right graph, many layers are squeezed into a twisted result and create a large Saint-Laurent. So it's very important to optimize the ordering of layers to reduce Saint-Laurents and improve readability. We propose the concept of composition to help ordering layers. Composition indicates the degree of how two layers mutually compensate their thickness change. The smaller the composition value is, the closer the two involved layers should be placed together. Note when the denominator is 0, which means that the thickness of both layers don't change at all, we will make the fraction to be 0. Apart from the composition degree between each two layers, we also take the thickness and the length of layers into consideration, which are not reflected in the composition degree. These two factors will help to prevent thickness jumps and distortions introduced by thin and short layers. This way, we get a distance function, which guides us how to order layers. Now, we perform a hierarchical clustering of layers using this distance function. In addition, a leaf ordering algorithm is applied to the involved binary tree to get the final ordering of layers. This is done by minimizing the sum of distance between adjacent layers. After ordering, baseline optimization is applied to get the final layout of the string graph. Let's go to the evaluation part. First of all, we did a quantitative evaluation of the effectiveness of our algorithms in reducing layer distortion compared with two state-of-art techniques. For different datasets, 3 ordering and 3 baseline optimization methods were applied to get 9 results in total. We compare them through 3 numerical metrics as well as measuring the time they take. The result shows that our method performs better than the others. Then we made a user study to test the efficiency of our method compared with 2 other types of string graphs. The users need to complete 3 tasks. They were required to read the thickness of layers, estimating the whole thickness of a string graph, and find the target layer in a graph that corresponds to a given layer. We record the accuracy and the time spent on the tasks and then did our analysis. The result shows that our method had better appearance compared to the others for both user accuracy and completion time. The following self-reported preference of the participants for aesthetics and readability also indicates that our method creates more visual pleasant string graphs with high readability. In addition, we performed a case study on real-world datasets to furthermore demonstrate the effectiveness of our method. The results was positive. The experts reported the lava layers were more smooth, which is pleasant and easier to read. The final is our conclusion. To conclude, we propose SunStream, a new string graph layout optimization algorithm that uses the sun illusion as the perceptual foundation and enhances the readability of string graphs by reducing it. We did a quantitative evaluation, a user study, and a case study to verify our algorithm's reliability. More details can be found on our website, and the source code of our algorithms is available on GitHub. Thank you for listening.
Hi, Joan. Thanks for that interesting presentation and the nice work that you did together with your colleagues. Very promising and convincing results that you produced. I'm still waiting for, there's a lot of applause going on. Cheers to you. By the way, we have 128 visitors at the moment. That's not too bad. Cool. As we are waiting for questions, I would like to start with one. A bit biased by my work with Michael Sedelmeier, who's, in my opinion, one of the masters of metrics in our community. I would like to add a question that is for the quantitative evaluation. Can you give a bit more details about the 3 measures that you used for your evaluation?
Oh, yes. In fact, there is a mistake in our slides. The three metrics we're using is from the other 2 works on string graphs, which then used to do the baseline optimization, which are the L2 norm-based optimization and L1 norm-based optimization, and the others is our baseline optimization with combine the sun illusion, and this is the 3 metrics.
Thanks for that. I must confess I was a bit distracted because the chat is now hot. I have a compliment by Christian Tuminski, who says, great to see that a long-standing InfoVis problem being addressed finally. Congratulations to that. And Michael is not that happy with being called masters of metric. Never mind. I would like to add a second question. Maybe you can ask very shortly. Did you discover situations?
Could you be a little bit slow?
I can do that. Sorry for that. Did you observe data situations where your technique does not produce a benefit, where the layout does not work that well?
Did you ask me that is there some bad situations that our algorithms don't work? Yes, that it's true. As a matter of fact, there is no accurate formula to estimate the impacts of sun illusion. We just get a formula through our mathematical results. In fact, if we want to get a formula that works for all situations, we need to do more user studies to know how to measure the sun illusion effects accurately.
Got that. And with this last question, I would like to thank you, Yuan, again, and we proceed to our last paper. We stay in Streamland and proceed to the paper which is called Split Streams, a visual metaphor for evolving hierarchies, which is presented by Fabian Bolte from the University of Bergen, where he works together with Stefan Bruckner. And he has 2 more co-authors coming from the University of Florida, which are Mahazan Noorani and Eric Regan. So let's get started with streams of evolving hierarchies. Here we go.
Hello everyone, my name is Fabian, I'm from the University of Bergen in Norway, and together with my co-authors Mersan Noorani, Eric Reagan and Stefan Bruckner, we want to present split streams, a visual metaphor for evolving hierarchies. Let us look at this simple hierarchy. Imagine a university, it employs a professor, and the professor supervises 2 PhD students. We have many ways of displaying this hierarchy. For example, as a node-link diagram, as an indented tree, an icicle tree, or maybe as a tree map. In fact, there exist quite many visualizations for hierarchies, and treevis.net provides a very good overview. Given this hierarchy, we can then visualize values changing over time. For example, with timeline trees, we could display how many papers every student published every year. Or with theme river-based approaches, like multi-streams, we could also see aggregated values. For example, how many papers did a department, the faculty, or maybe the whole university publish? But what if the hierarchy itself changes? What if a student wants to have a new supervisor? Or maybe the student wants to switch from computer science to philosophy? Well, the easiest approach is to display hierarchies next to each other. For example, here we see 3 tree maps shown next to each other to display 3 time steps. The student, shown as a white node, switches from computer science to philosophy and back. Or maybe he switched to philosophy, quit, and another student started studying computer science. It becomes clear that displaying hierarchies next to each other does not display all the information that is in the data. And if we want to resolve this issue, the representation becomes cluttered very quickly. And several approaches try to resolve this issue, and I want to focus on 2 of them. First, the nested tracking graphs by Lukaszek and others, as well as Chronicle by Wittenhagen and others. Both of these methods use a very similar approach. I will demonstrate it for you. Let us assume we display a tree map for every point in time, and we remove the node separation along the x-axis. Then we set the width of every tree map to 0. If we connect the nodes of the hierarchy via Bezier curves along the time axis, we receive a stream-based approach similar to those of Lukaszek and Wittenhagen. Although there exist different terms for this visualization, I want to refer to them as nested stream graphs. Although this representation displays the changes of the hierarchies very well, it comes with a significant drawback. And I want to demonstrate it to you by asking a simple question. How many nodes do you see in this hierarchy? And I hope you had a bit of trouble, but maybe it gets easier if I display the same data as a tree map. The problem with nested string graphs is that by connecting the hierarchies along the timeline, we lose one dimension of node containment. And what I mean by this is that the nodes are still contained by their parents along the y-axis, but not along the x-axis. So now we have 2 visualizations, one displaying changes of hierarchies over time very well, but having problems to display the hierarchy itself, and the other displaying hierarchies but having problems displaying their changes. Would it not be great to have one visualization with a clear representation of the hierarchy and its changes over time? Let us go back to the creation of nested stream graphs. But instead of reducing the width of the tree map to 0, we give it a fixed width. We again connect the nodes along the time axis and receive a stream-based representation. We call this ratio between space used for the hierarchy and space used to display changes the hierarchy change ratio, or HCR. An HCR of 0 only displays changes, while an HCR of 1 only displays hierarchy. Additionally, we call the separation between a node and its parent X margin. With that, we have sort of achieved an interpolation of tree maps over time to nested stream graphs. We can now reintroduce the X margin to highlight the hierarchy, and we call the position where the X margin is applied a split. And we call this visualization a split stream. But this is not all, because we have not yet talked about node values. Let us assume the height of a node represents the number of papers that a student or a professor published in 1 year. The professor is a co-author on all its student papers, and that is why its value is the sum of the student papers plus the papers that the professor wrote himself. If we display this data as a nested stream graph, it will look as expected, as both students are contained by its parent node. But if the professor was lazy and did not publish any papers himself, his node value will be the sum of all the student values. In this case, representing it as a nested stream graph leads to the professor being completely covered by its students. Now we have two options. We can artificially increase the size of the parent node, or we can decrease the size of its children. We call these changes in value Y padding and Y margin, respectively, and I will now demonstrate the changes between the two. No matter how much we increase a parent node, its children will always have a value greater than 0 and therefore be visible. But if we decrease children sizes, their nodes will reach 0 and disappear. We can use this method as sort of a semantic zoom to focus the user's attention to certain nodes. With this definition of our visual metaphor, we can create quite a number of visualizations. We can recreate tree maps over time, stream graphs, nested tracking graphs, split streams, and even storyline visualizations. So what are the benefits of our method? In this example, we are looking at the Allen Developing Mouse Brain Atlas. What we can see here is the mouse brain at certain points in time, and we can see the size of individual parts. If we display this data as a nested stream graph, we get a better impression of the development of certain parts of the brain. If we additionally apply our split streams method, we can also see the underlying hierarchy. By zooming in, we see that the mouse brain is split into 4 main parts: the spinal cord, the forebrain, the midbrain, and the hindbrain. We therefore manage to include both the changes of parts over time as well as the underlying hierarchy in a single visualization. In our second example, we are looking at the taxonomy of medical subject headings. This taxonomy includes about 60,000 medical terms and was updated over the last 20 years. Specifically, we want to look at one branch of the taxonomy that is called the urinary tract. We can see how certain terms were added or changing their position over time. I have highlighted 2 nodes of the taxonomy in orange, and they look surprisingly similar. When applying our split streams method, we have an easier time comparing these nodes, and we can see that they only differ in the first and the last time step. Additionally, we get an impression of how many time steps we are looking at and how many nodes there exist in the whole hierarchy.
In order to evaluate our method, we ran a user study on Amazon Mechanical Turk with 120 participants. Every user saw exactly 1 out of 3 methods of visualization and answered 13 tasks. The visualizations were tree maps over time, nested stream graphs, and of course our approach, split streams. We hypothesized that tree maps over time and split streams both would give users an easier time in understanding hierarchies compared to nested stream graphs. This is due to the node containment of 2 dimensions. Secondly, we expected stream-based approaches to provide better performance for understanding changes of hierarchies over time, simply because these changes are not reflected in tree maps. And finally, we expected stream-based approaches to ease node value comparison. When the participants started the study, we provided them with instructions based on their given visualization type. They then saw 3 examples and 3 practice trials. In those, they saw a visualization, tried to solve the task, and after their attempt, they were given the correct result and an explanation why it is correct. Then they had to answer the 13 tasks in random order plus one attention check question. We based our study on a file system scenario. One possible question could be, in January, how many folders have at least 3 direct subfolders? In this case, the user sees a split streams, and the answer would be 2. The participants had an unlimited number of attempts to find the correct answer. We measured the time they spent on their first attempt, the error of the first attempt, the total time for the whole task, and the amount of attempts they needed to find the correct answer. We found a number of statistically significant results, and if you are interested in the specific numbers, then please refer to our paper. But let me highlight the main findings. We found that users, given the tree map and split stream representations, made less error on their first attempt and required fewer attempts to find the correct answer. On the other hand, users, given one of the stream-based approaches, required less time to finish their first attempt and also required less time in total to get the correct answer. We can see that our split stream methods manages to combine both representations and their individual benefits while avoiding some of their individual shortcomings.
For this reason, we consider our method a general purpose visualization for dynamic hierarchies, with a clear representation of the hierarchy and its changes over time. We did not address the scalability issues of nested stream graphs, so we are still limited by the number of time steps in the nodes that can feasibly be displayed. However, by revealing the underlying hierarchy, we also improve the interaction with some of the underlying nodes. Finally, our method is openly available with about 1,300 example datasets. You can also find the complete survey and its results from Mechanical Turk on GitHub. And with that, I want to thank you, thank my co-authors, and thank our funding agencies. Right now, I'm looking for jobs in the US, so if you have any open positions, then please get in contact with me.
Good news, Fabian. The audience is happy, many claps, while I'm waiting to get questions, I would like to start with the first one. I personally like the idea that you have 4 parameters which define how the visual representation will look like at the very end. And the animations that you showed, the transitions by interpolating these are very impressive. Can you imagine that different users would prefer different parameter settings?
Yeah, I could totally imagine that, similar to how the questions we previously saw, how some users might prefer bar charts over smoothed lines. I could also imagine people preferring tree maps over, well, smoothed out lines. For many of these parameters, though, it depends on the data set, and for some parameters, you need to have them at a certain value to see all the data that's in there. So we discussed this a little bit in the paper. For example, when when the hierarchy is too deep and the space between one time step to the next is too narrow, then you might not see, well, so far deep into the hierarchy as you might want to.
So then the padding and the margin parameters would be critical, I guess.
Yes.
I can imagine. Second question is an inspiration question. Could you imagine that you make these parameters user parameters in an interface, and then users could interact with it and come up with their solution?
Oh, this is already the case.
I thought so.
As we've shown, the source code is completely available, and we also have a running demo online where you can inspect all the data sets that we used and also play around with the parameters yourselves. But the question is always, since this is more, I would say, more a visualization for the masses, the question is always how much of the parameters do you even want to reveal?
Of course, which is the everlasting story of parameters, of course. A question that is implicitly been addressed by you already comes from the audience about the number of hierarchy at the depth that you can, how many levels that you can address.
So There's some music in the background. I don't know. Okay.
That's my fault. I'm sorry.
Yeah, that's very confusing. So the number of hierarchies we can handle. Basically, you can choose the distance from one time step to the next, and you can choose the space between that you give to a single hierarchy level through the margin. And with this idea, you can theoretically have an infinitely large hierarchy, but then again, it also depends on the height of your chart and the monitor you're on. I don't have any specific numbers in mind right now. Maybe it's easiest to check out the demo and try out some of the examples yourself.
Sounds good. Also, thank you for pointing out that the tool is available. That's something that I wanted to say as well, as it is very important, and also my personal opinion that something like this should be yes, declared. I have one last question regarding edge crossings. How is your opinion on edge crossings and the number?
Yes, so I mean, as we know, typically in these stream-based approaches, you want to reduce the edge crossings to make the chart more readable. For a follow-up project that we also published, we already used the Sugiyama algorithm to reduce edge crossings on a heuristic. There's also an interesting approach in the temporal tree maps paper that we wanted to apply for the nested tracking graphs, which is not yet, which would need some modification to be applicable to our application. But we definitely thought about that.
Thanks for that answer. I was distracted by yet another question that came up. I just copy-pasted it. It is, how does the padding work if the tree is unbalanced? Is there a way to get around the propagation of the padding error? Does it look good? Maybe the session is forced to be ended. We are 7 minutes over time. So let me conclude the session, first of all, by thanking all the speakers and all their contributions to that and the presentations. Thanking also for the technician who did a great job in supporting us. Thanks for the audience for being so chatty and in such a good mood. I liked it a lot. And this sort of concludes the session. I would like to say one last sentence about this mirror thing. And this is it for today. Thank you very much for attending the session. Love to see you in the next days. I'm handing back over to the technician.
Rendering large volumetric datasets is still a challenge for real-time applications. Wouldn't it be nice if you could just render the dataset at a low screen resolution and your neural network upscales it to the full resolution again? We proposed a network architecture that does exactly that and can outperform a full resolution rendering for large datasets. For quantitative and qualitative evaluations, come to our talk.
The make of continuous color maps. We present the CCC tool, a new web tool for the creation, editing and analyzing of application-specific color maps. For the precise definition of color maps, we developed a new color map specification. This new structure increases the editability by reducing the numbers of colors to a minimum.
Usual collaborative systems propose a public and private environments, the latest possessing visibility rights. Subjective views are special objects perceived differently per user. However, a break in the social space may happen during exploration. Our visualization context strives to link efficiently multiple related visualizations together around a common object. We discussed about the designs of a stacking layout, virtual linking layout, and a mix between them.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Comparative layout are the visualization arrangement to support visual comparison tasks. To better understand them, we conducted a systemic survey on 127 research papers. Based on the survey, we suggest a lucid classification as well as diverse practical implications that help you better design comparative visualizations. Find out more in our presentation.
Providing insights is the main purpose of visualization. A lot of systems automatically communicate insights to users, but we don't really understand a lot about the space of these automated insight tools. We conducted a review of 20 automated insight tools and proposed a framework of the types of automated insights and the purposes of providing auto insights. Take a look at our paper to learn more.
Typically, black hole visualization takes a lot of compute time, but we achieve a quite faithful reproduction at interactive rates on a standard computer. For this, we make use of a novel adaptive grid approach to focus calculations where needed. Coupled with filtering and interpolation methods, we can obtain high-quality imagery. Our approach accepts star catalogs and environment maps and generates the resulting deformations in real time.
Many real-world analysis environments involve multiple types of experts and analysts working together. We aim to provide new knowledge about the role of provenance in a variety of data analysis scenarios. We present the findings from interviews with the data analysts from various domains. Our results demonstrate how different needs for provenance depend on different analyst roles and also helps to identify possible opportunities for advancements and new techniques for provenance support.
We present 3 external labeling concepts that allow a user to browse through point sets without the need of zooming in and out. In the first method, labels are distributed on multiple pages. The next method arranges the labels in a single row that can be continuously slid along the bottom side of the map. In our third method, labels are distributed on stacks, which a user can independently browse through.
In interdisciplinary visualization research, scholars browse collections of scientific papers searching for existing methodologies that can be imported into their own domains. In this short paper, we implement a document exploration prototype that employs distribution and similarity between author-assigned keywords to detect potential methodology transfers between 2 collections of research papers. If you want to know more, please read our paper.
What is insight? It is a question that has bothered visualization researchers for a long time. We're wondering whether visualization practitioners think about data insights in the same way as visualization researchers do. So we interviewed 23 visualization practitioners to understand how they think. To find out more about what we found and the implications to the visualization community, take a look at our paper.
Large displays are beneficial for visualizing vast amounts of data. However, there are challenges regarding perception, personalized views, and managing data complexity. To address these issues, we propose to combine large interactive displays with personal augmented reality. We present a design space, as well as several visualization techniques, such as curving the whole screen, embedded visualizations, and many more.
We propose a novel vision analytics system for optimizing bus networks. The system helps users first analyze bus network performance and identify problematic routes. Then, the alternative to a selected routes can be obtained in real time. By evaluating these routes with our system, the users can efficiently decide which one is the best and improve the bus network.
University directories routinely become outdated and often lack the information necessary for understanding a researcher's interests and past work. To assist in the exploration of research talent, we have designed PeopleMap, an interactive tool that maps out researchers using NLP techniques. By using PeopleMap, users can explore the diversity of research at an institution and identify potential research talents.
Dimensionality reduction is an important tool for the visual exploration of complex high-dimensional data. Most existing techniques focus on preserving the intrinsic geometry of the data during the projection. However, important information can be encoded within the global structure of the data. To address this, we present TopoMap, a dimensionality reduction method that provably preserves the topological features of the data during the projection.
Although prior work has examined how visualization impacts decision-making, there is no concrete method for quantifying and comparing the impact of different encodings on decisions. We rethink how we evaluate decision-making with visualizations by leveraging work from economic theory. We present the results of a large-scale lottery game that evaluates the impact of 5 different visualization designs on risk behavior and decision-making.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
This study presents a method to explore hierarchical data by improving ROD-VIS, one of the visualization techniques for multidimensional data. The user can set options for nodes and check the data in groups or individually in the ROD-VIS. 3 subviews at the right enable the hierarchical clustering structures of selected data and allow the user to grasp the features of selected data. As a result, this system allows more detailed insight into the data while solving the node overlapping problem.
We propose a novel visual analytics system for optimizing bus networks. The system helps users first analyze bus network performance and identify problematic routes. Then, the alternative to a selected routes can be obtained in real time. By evaluating these routes with our system, the users can efficiently decide which one is the best and improve the bus network.
DataBreeze is a multimodal visualization system that lets people interact with unit visualizations using pen, touch, and speech. By supporting multimodal interaction, allowing users to manipulate, refine, and customize the view, DataBreeze enables a novel, fluid, and flexible data exploration experience, enabling a seamless transition between global and local level data exploration, spanning the entire dataset or a subset of the data.